Hi, I'm Matt Squires. Just to introduce what I'm working on, the thing that we typically align with our lasers is fiber optics. So I work in a lab that uses a lot of lasers, and we have to then move that laser light around to someplace else. And if you haven't worked with fiber optics before, it's typically a piece of glass. It's a glass fiber, and down the center of that fiber is a different index of refraction. And typically and we call that the core. So the light is guided in the core of that fiber. And when I was trying to think of what it would relate to, typically there are two types of fibers. One is called a multi-mode fiber. It's kind of like a superhighway. It has a lot of width that you can pump a lot of, or not pump, but put a lot of light down. But it's not very organized. Each photon is like each car on the highway, and it can basically go wherever it wants, and the light that comes out the other end isn't very organized. The other type of fiber that I typically use is called a single mode fiber. There's space for one mode of light to go down the fiber, and it makes it so that the light fiber is about 60 microns. That's about the width of a human hair. So if you look at one of your hairs on your arm, or if you pull one out of your head and you look at that, you think like, okay, that's pretty small. But if you go to a single mode fiber, it ends up being about 1/10 of that size. So you imagine taking a human hair and dividing it by 10. And that's the size of the core, the light guiding inside of that fiber. And that's pretty small. And what we need to do is be able to hit that, and that's the target. So that's not even the bullseye. That's just the target that we're trying to hit, is that few microns in there. And so what we're trying to do is have a better way of coupling that light into that core and being able to do it in a way that's repeatable, and then also doesn't have a history associated with it. So this hysteresis word means that there's a history. So if I move some alignment fixture, it doesn't always come back to the same place. It depends on the history of where I've moved it. And so go to the next slide. So I worked on this with two students. They were both summer students. We have a great summer student program. Esteban Nunez was actually a high school student when he started working on this, and Kai Rogers was an undergraduate student that came for the summer. And so we started looking at how we can use these prisms instead of what's typically used, which is what's normally used as a mirror. You take the laser, you shine it onto a mirror, and based on how you rotate the mirror, you'll be able to control the position of the light. And so we're looking at using these prisms. So next slide. So it roughly looks like this. We have two prisms. We send light, which is blue in this who is trying to adjust and fit eyeglasses to people. So he was using it for eyeglasses, but what we were looking at was, what is the mathematical formulation of this? And then can we use these multiple Risley prisms in order to be able to position light to couple it into this very small fiber optic? And so this is the innovation, that we're using it in this way to couple into fibers, and we've developed this mathematical theory that simplifies what the alignment and the rotation of the prisms need to be. Next slide. And so again, as I said, the background is that we have this work that we're doing in the lab. We're trying to use lasers as a tool, and oftentimes what we end up spending most of our time doing is every morning coming in and adjusting the lasers, and we'd really like to have a setup that is much more robust. And the typical solutions, as I said, were to move a mirror, or another option is to actually try to move the lens in front of the fiber. And these become very temperature sensitive. So if, say, the air conditioner was having a bad day, we often is a day that we can't use our experiment because there's enough change in that positioning that the thermal effects in the lab move that laser off that like 1/10 of a human hair position that we have to be maintaining. So we're trying to have that alignment. And this is not just for us in the lab. There's definitely other users and other labs that have this issue every single day. Actually, in COVID, because students were so used to going into the lab and having to tweak up their experiments, that they came up with all of these backup solutions in order to align their experiments. And most of those were just putting motors on their mirrors. Next. So again, I think I covered most of this. There's a lot of places where people need this very precise alignment. I very much think about the fiber optic solution, but there are other places where people need to be doing very precise alignment with fibers. Next slide. Most of the people that I know of that need this are in the lab, but I believe there are other applications out there where they can be using this. Next slide. And so here's some of the results that we have out of the lab. The circle is just us moving one of those prisms. The green is what we predict from our theory, and then the crosses are the actual data. The two lines on either side, you know, the smaller and the larger circle, are actually the tolerance of the optics that we get from our company. So they have some tolerance associated with it. So it looks like they did a pretty good job making their optic, and it looks like we did a good job matching up. And then if you rotate one of the prisms faster than the other prism, you start getting these kind of pretty flower shapes. And then again, the solid line is theory, and the points are where we measured that we line up. And so we line up pretty well with that. Next slide. So we've patented this, and we're building a system for lab use to show that we really do get this kind of long-term stability. This is not related to my main area of research. It's more, again, trying to make it so that our lab is easier to run. And so this is typically a summer student project that every summer I have a student take it to the next step. So we're to the point where we'll have a summer student hopefully be testing the actual stability of this. And we're looking for people that could use an alignment system.
Customers might be, because there's got to be some out there who, obviously the telecom industry probably has a lot of factories where they're trying to do fiber alignments by the thousands every day, right? Wouldn't this be a good place to start?
I believe so. I think typically the telecom industry wants something that's really small, and we just haven't figured out what the size limitations are yet. But yes, I believe so too. I was talking to somebody that was also in like a high power laser industry that was doing laser welders and things like that, and they often had rules of thumb that when you went from one part of a laser system to another, you basically assume that you lose about half your light. And I think some of that's just due to alignment, the inability to align. So I think there's telecom. I think there's also these like high power
laser manufacturing.
Yep.
Yeah, interesting.
Yeah, to piggyback on Chuck's line of questioning, I feel like I'm left with the question, so what? As an investor, as a layperson, I want to know what specific problem is this going to solve that matters? And my head goes to driving and sort of safety. That's even possible, or maybe even surgical procedures where you need that precision. So I would encourage you, if you are in fact out looking for capital, looking for strategic partners, to really hone in on some of these problems that we can relate to, because I think that'll sort of enliven the presentation, make it more fundable. Again, if that's what you're looking for, I'm not entirely clear that you're out looking for capital, but those are some of the questions that I would encourage you to hone in on.
Thank you.
No, thank you. This is, super fascinating. I feel like I've learned so much today, and this adds to the knowledge in at the telecom market, has there been, maybe development on more so of like who are the competitors? How do you, disrupt the market space?
Yeah, great thought.
So I'll wrap things up here real quick. If you're not looking for an MBA intern, maybe you ought to think about that this summer and get somebody out there to really explore a few of these applications. I thought the medical device, lasers are used so much in medical procedures, and so there's just some great big problems that potentially this could really solve. And the first step isn't to say, hey, do you want to buy a bunch of these, or here's what they look like. It's to figure out what those requirements would be for these different industries, because there may be one where they don't care about size. Maybe the manufacturing application, for example, big is fine. Maybe medical they do, but if you just do a little bit of homework, I think you may find that you're sitting on something that's extremely valuable to a bunch of different industries.
Great, thank you. There's a question from the audience.
That's about 50% of what setup and changeover problems are, is just there in the calibration step. So I would support that you want to look at what industries, for instance, might be trying to stitch imagery together. Because, movement when you're taking the image over time is a major gain for anybody who has high dollar, let's say, doctorate machine tenders, right? That doesn't pay. So you might look for that kind of a scenario as well.
Great, thank you.